Dear all, welcome all of you. So we'll start our session within 1 2 minutes. All right. So I'm Vijay Rane, and today we are here to discuss some of the problems on the retrosynthesis. And mainly, as you know, from the last week we have started the some problem based on the which has the molecule which has the chiral centers, and we are slowly moving to the to get some solve some problems which involve uh, the stereochemistry in their final product. And we'll see some retrosynthetic examples in this class before going to the start our session. So do you guys have any doubt regarding the topic which is covered by the professor, or or regarding the basics in this retrosynthesis? We have already covered in the week one, the first week, that is on the why this retrosynthesis is important and his historic perspective in the organic synthesis, and also saw some of the terminologies used in the retrosynthesis, mainly the disconnection approach and the functional group interconversion. And in between, as upon the request, we have also studied some oxidizing and reducing reagent, some reaction associated with the oxidation and reduction. Mainly because in our day-to-day this retrosynthesis, in our retrosynthesis course, it is important to know multiple some chemoselective oxidation and chemoselective reduction reactions. Further, we have also slowly started uh, s- the problems which involve the stereochemistry. Why this it is important in, the to do the understand the stereochemistry based problems, or why it is important this asymmetric synthesis. This asymmetric synthesis mainly the synthesis which mainly deals with this the chiral molecules which has the chiral center. This is mainly because if we look at the this dopamine, the L dopamine is used for the Parkinson disease. However, this the D dopamine, which is particularly toxic to the human body. Similarly, if you look at this molecule, so this molecule is mainly used for the microgram, trap the thousands of beetles. However, retain 10% activity, and only even 1% of his compound destroy the activity. So if the compound is impure, then this can be destroy the activity of uh, this active compound. So impurity of this compound, which only impurity mainly associated with the this chiral center. So therefore, to have this molecule, we need to the this molecule in pure, and that's generally uh, comes from if you do some chiral synthesis, then only it is possible to get the in pure this compound. And here, this is the and few molecules. This is the one molecule which is S citalopram. So this is the antidepressant. However, this R citalopram, which is inactive, and there is for this molecule there is no known any hazard reported so far. However, as we see in the case of the the L dopamine and the D dopamine, so D dopamine is particularly toxic. So in some case, it is okay to have this in a have some impurity of some side product. or some enantiomer in the API. However, in cases like this dopamine, uh, slight impurity can cause the toxicity. So in this regard, we have seen the stereospecific reaction and also some examples of the stereospecific reaction in the last video. So I will just quickly revise this one. So the stereospecific reaction mainly uh, the reaction which mainly gives the particular only one product. So that reaction is called as a stereospecific reaction. The example is you can remember the example SN2 reaction. So in the SN2 reaction, we get the 100% inversion in the comparison product. What is the stereoselective reaction? So the stereoselective, if I shown some example of the stereoselective reaction, so which is this example, particularly which example will be best suitable here. So yeah, so this is the example of a stereoselective reaction. So the epoxidation of the such type of bridged systems. So you can see, so we get the major isomer of this, which is the exodirecting. Why? Because the attack on from the downside of this one is sterically hindered, and therefore we get the epoxidation, particularly exodirecting. Also, we get this minor product formation. So this type of reaction we call it as a stereoselective reaction. So we get the major and minor, both the product, which is not in the case of stereospecific reaction. So that's the minor difference. If you look at the another example here, so on the reduction of this ketone, let's say by using the lithium aluminum hydride. So what happened? Due to this bulkiness of this methyl group present on the adjacent carbon atom, the attack of the hydride on the top side of the side on which the methyl group is attached, which is hindered or the, somewhat sterically hindered, and therefore we are getting minor product formation, this one, so which is 24%. However, the attack from the bottom side, which is sterically preferred. Why? Because there is no any steric route as in case of the top side above attack from the methyl group side. So therefore, we get the major product formation in this case, in which the hydride attack on the bottom side, and we get the major product formation 76%. So that's what. So this is we get the major product and another also minor product. So this is like a we get some selective product here. So we can improve the selectivity. So the improvement of selectivity, you can see the example. Instead of lithium aluminum hydride, we can, if you add some more bulkier groups, we can bulkier reagent or the bulkier hydride source. So this is diol H. So this diol H stands for diisopropyl butyl hydroxide, and due to this diisobutyl group, the bulkiness get induced in this reagent, and the hydride transfer from the top side now, which is nearly impossible. Why? Because this entire hydroid transfer group is now quite bulky, and therefore this stereochemistry of this methyl group, due to this stereochemistry of this methyl group, the attack on the top side is not favored. So the attack from the bottom side is more preferable here, and we get almost 100% formation of the attack takes place on the bottom side. So this is the example. So we can improve the formation of the two product by in this stereoselective reaction. That is, we can improve the selectivity basically. Another example, as you can see here. So in this case, what happened? So there are two different type of reactions. So the dash and so the first reaction is the reduction of this alkyne with the H2 palladium complex and the influence of the barium sulfate salt. So we get the formation of cis product as a major product uh, and the trans product. So in this case, the trans product as a minor product. However, when you use the butyl lithium, sorry, liquid ammonia and the sodium metal or the lithium metal, in that case, we get the transalkene formation of the product as a transalkene as a major product. Why? Because the direct this addition, as I mentioned last uh, video also. So the mechanism of this reduction reaction is different in the H2 palladium or the H2 metal reduction. So this type of reaction progress goes. So this is the metals of metal, and hydrogen first initially bind to the metal, and the cis hydride transfer takes place to the olefin. So in this case, we have the alkyne. So this will be the cis. So cis, since it is cis alkyne, so there should be only like this. So addition of the hydrogen in place of the metal catalyst takes place in the same fashion. So therefore, we are getting uh, cis as a major product. However, in case of the liquid ammonia and the in case of liquid ammonia and the in case of liquid ammonia, sorry, liquid ammonia and the sodium metal. So this reduction takes place via electron transfer and by the radical mechanism. And in this case, we are getting the major product as a transalkene. So you can see here transalkene we are getting as a major product. So the so these are also the example of the select diastereos. This is example of the stereoselective reaction, and particularly it this is the diastereoselective because so the form product we are the diastereomers to each other. So therefore we are calling it as a diastereoselective. In some case, as you can see, this the example that we have seen for this uh, lithium aluminum hydride reduction. So in this case, since there already one chiral center was present, so this reaction also called it as a diastereoselective reaction. When there is no any uh, other chiral center present, that time it can be a enantioselective reaction. So the form product are if they are enantiomers of each other, then the reaction we call it as an enantioselective reaction. And further, we have seen the difference between what is the stereoselective reduction reaction, also the stereoselective and the stereo specific reactions, not the reduction. So in the stereo specific reaction, as we see already seen, we are getting only one product formation and gives the specific product formation. Mainly the formation of product mainly depends upon the what type of reactant we are using, and that's what final product depends upon the stereochemistry of the reactant. But in the stereoselective, so depends upon the reagent condition and several other factor as we see in earlier example. So the stereochemistry of this methyl group decide the formation of the product. So there are several factor depends upon the selectivity. Reagent conditions also we can see. So in this case, the reagent conditions are only different. So that can also drive the selectivity in the reaction. So these are about the stereoselective reaction and the stereospecific reactions. So now we will see more to the further some advanced part in this asymmetric synthesis. So I will add some slide here. So how this asymmetric synthesis generally uh, done. So before directly moving to the retrosynthesis problem based on the asymmetric synthesis, we need to understand particularly how the asymmetric synthesis works. Then only we can able to solve the problems which involve the uh, retrosynthesis, which involve the asymmetric synthesis or the which involve the chiral centers. So in this asymmetric synthesis, to access the enantiomerically pure molecule for biological application as a drug or the sweetener or the moisturizer, there is a need for adoption of efficient strategy, and there are several strategies are there. So there are three key important strategy to achieve the enantio pure compound. So you have to keep this remember. The first strategy is the use of the chiral pool synthesis that we will discuss one by one. So right now we don't really need to worry about what is the chiral pool synthesis or what is the second one, which is the chiral auxiliary approach, and the third approach is the resolution. So based on this terminology, you can see what is chiral pool. So in short, I can show you. We can use the chiral starting basically and carry that chiral center to the end product. So that will be uh, uh, chiral pool synthesis. Chiral auxiliaries, we can add some in between uh, adduct to our starting. That we refer as a chiral auxiliary. Basically, auxiliary, you can, from the word auxiliary itself, it is clear. Chiral pool means that is basically we are pulling this chiral center from the starting to the product. And the resolution method basically this is mainly deals with the not to nothing to do with the synthesis. However, this resolution approach is like we can do the purification of this from two intermediates. So basically let's say I have performed some reaction. So let's say this is the A, B, C and D. So this is directing upward, and another, let's say this B. So this B directing, sorry, this A directing downward. So what I am getting in my reaction, so these two are in plane. So I will draw with these two are with the different color, the T. Okay. So what is difference here? So the difference is very minor. You can see in this starting, the B is directing upward, but in the product, A is directing upward and B directing downward. So in my reaction, let's say, what I have did, I had something like this. Let's say A, B, C. I perform reaction. I got these two product. So this is the product X, and this is the product Y. And now in my reaction mixture, I have the combination of these two products. So in the resolution method, what we can do, I use the some purification method in a such a way that I can get this compound X in separate this compound Y as a separate. So we can get, if I get these two compounds separately by in the process of purification. Resolution basically purification. So that method is will be the resolution method, and so that also is one of the method to get the enantiomer pure final compound. So ultimate aim is our we need a enantiomerically pure final molecule. Whatever application, but we need a enantiomerically pure compound. Then we can use these three type of approaches: chiral pool, or chiral auxiliary, or resolution method. And resolution method is simplest one that I have already as mentioned here. So in my reaction, I am getting the product. So so let's say in my this reaction, so whatever XYZ, whatever the reagent I use, I got these two type of product. And in this reaction, so these are the product. So I need only the, let's say, X compound. Then I can, if I use the purification method and I am able to isolate this X and Y in these separate from each other and in two different able to separate this one. So this method in the resolution, and so we can use this enantiomerically pure X for our whatever application that we are aiming for, right? So in this way also we can get the enantiomerically pure compound. So this is the resolution method, and I will just I will not cover all what is the in detail this method, but I just highlight. So in this resolution method, what we can do, generally people do, they can use the chiral column. So you know the we can separate our product by using the column chromatography. So if you use the column in such a way that if you use the some chiral column, so in that case what happen? So this is the enantiomer X and this enantiomer Y. They behave separately or distinctly on the chiral column, which is not case in the normal silica column, right? In the silica column enantiomer we cannot really uh, separate this A and B, sorry, this X and Y, these two enantiomer from the normal silica column. If you use the chiral column, then which has the basically some binders and binder different functional group, they interact differently with these two different enantiomers, And then therefore the retention time or the elution time for this A and B from the column will be different. Let's say this compound come in the initial, let's say 1 minute run. I'm talking about the HPLC in initial 1 minute run, and let's say this can come from, let's say, 2 minute after 2 minutes. So basically for the first minute we are getting one enantiomer, and another in the later we are getting this another y enantiomer. So by this method we can basically we get the enantiomerically pure two compounds in hand by this approach. Also another approach is like what we get the chiral two different enantiomers in our reaction mixture. What one can do, we can make convert this product into the diastereomers. So let's say this B functional group is basically acid. So what we can do, I will add in the in another slide basically. So let's say I am getting these products, right? Now what I can do for the to get this product, I can convert this functional group. So let's say my this B functional group is carboxylic acid. So in that case, I will show you OH, and what is here. This B functional group is carboxylic acid as I mentioned. So what I can do, I can add some chiral alcohol on this one. So let's say this is chiral, uh, let's say CH3, and here anything like phenyl and OH. So this is my chiral, initial chiral pure alcohol. Chiral pure, I am talking about chiral pure alcohol. So this is the pure, let's say this is 1, 2, 3, R. This is ROH, R, whatever alcohol. So this is enantiomerically pure alcohol. What I can do, this is present in the form of mixture, right? So I convert this into corresponding. These are the enantiomer. At this stage, they are enantiomers, and we know enantiomers are inseparable by column chromatography because uh, they don't have any what we call there is no any RF difference in this for these two enantiomers. But now what I can do, I can treat this reaction mixture with the this alcohol and convert this. We know this alcohol plus acid plus alcohol. What we get the ester, right? So this is basically R. So this is the R, right? Let's say R1. Okay. So we are getting the ester in this reaction. Alcohol plus, sorry, acid plus alcohol, we are getting esters. But now what happen when you do the uh, esterification reaction on this reaction mixture, we are getting basically, this is now, let's say, I get one and two different esters, but now they are diastereomers of each other. Whatever the two esters that we are getting in this reaction, so these two esters are diastereomers of each other. So whatever this I mentioned, this is the X, this is Y. Now what I get in this reaction, I am getting now this X ester, right? This X ester and the Y ester. So they are now diastereomers of each other, and now they are very easily separable from the by using the column chromatography. And later again we can do the uh, ester cleavage to get the alcohol back. So that's also one procedure, right? Esters Now at this stage we can purify these two esters, and once we purify separately these two esters, so now we have these two pure esters. So we know we can do the ester cleavage of this ester. So that I will show in the another slide. So you know the reaction. So let's say I have such esters OR2. So we can do the convert this ester to further back to the acid. So now, so that's what I am saying. So as I mentioned, X ester and Y esters. So we have purified that X ester and Y esters separately. So if I want only the chiral pure X esters, so from the acids that our desired product. So what was our desired product? Our product was this X molecule, right? With this initio pure X or Y molecule. So we can do uh, convert this ester to corresponding acid, right? So now we are getting back this acid back. So let's see D, whatever it is. This is A, right? So basically, that will be a two-step additional we need to perform. First step is the convert this enantiomeric mixture into their corresponding diastereomers, and at this diastereomer stage, purify that diastereomers, so they are separable from each other. So once we purify these diastereomers, so now we have added ester functionality. So we need our acid back, so we can convert this ester to the corresponding acid by just the hydrolysis of these esters, right? So in this way, basically, this is also one method for the resolution. There are several methods for resolution, but at this course, we are not really focused on this resolution. We have to mainly focus on these two other strategy, like the chiral pool asymmetric synthesis and the chiral auxiliary approach in the asymmetric synthesis. Any doubt in this resolution method? If you have any doubt, please let me know. We can discuss that one in detail, maybe.
Sir, hello. Hi, sir.
Yes. Yeah.
Sir, I could not understand. Please repeat the session if possible.
This mainly this from here, the what is the resolution,
Yeah.
or from
This is
okay.
your slide number. This is slide number 19, na?
Okay, sorry. Regarding the stereospecific and stereoselective reactions as well.
Yeah.
Okay,
If possible, sir.
we can
I
quickly have.
changed my device. I could not give proper attention. So
Okay,
after that,
so basically, we'll again, because this is somewhat complicated. It is very common to face difficulty in the understanding this asymmetric synthesis. So why it is important asymmetric synthesis? So before studying, we need to know why we are studying asymmetric synthesis. So first of all, if you just compare this one first example of this dopamine, so this L dopamine and the D dopamine. Difference is only the stereochemistry of this uh, amine functional group, right? So only this difference between these two functional group, this L dopamine cures the Parkinson disease in the human. However, this D dopamine is toxic to our body. So let's say we are getting these two products. There is only difference in the chiral center. So if you do the normal routine synthesis, in our routine synthesis, what we get? We get the mixture of this product. And if we have this mixture of the product, so basically, when we are doing the some a tablet for cure this Parkinson disease, if you are taking some tablet, then what happen? So this D dopamine can also go in our body, and then it can cause the toxicity. So therefore, we need the initio pure this L dopamine. So therefore, it is important to study this asymmetric synthesis. Further, other two examples are also the showing the same. This is not always the case. That is, the other enantiomers is the toxic. So there are several duct. If you just Google it, there are several duct. They can be uh, in the market in the enantiomeric impure form. I am saying enantiomeric impure means there will be some sort of other enantiomers, but in that drugs, these other enantiomers are not much harmful. So therefore, they are solding as it is in the enantiomeric impure form. But as in case of this dopamine, so we cannot really sell this drug in the form of this racemic mixture or the enantiomeric mixture. So we need very enantiomer this dopamine. Otherwise, small impurity of such uh, another enantiomer can cause the toxicity in our body. So therefore, the synthesis in all the chiral centers, it is important in terms of the medicinal chemistry. So we are studying here the retrosynthesis, and so we are slowly moving toward the retrosynthesis of these some chiral molecules. So before going to directly to retrosynthesis, I want to understand some basic concepts. I want to you guys to understand some basic terminology, mainly these stereo specific reaction and the stereo selective reaction. So first we will see the what is stereo specific reaction. The specific reactions mainly we are getting only one product. So there is no choice. So if you read this statement, so the reactions where mechanism means the stereochemistry of the starting material determines the stereochemistry of product. And there is no other choice. We are getting the 100% formation of the final product. So basic example, the SN2 reaction. So what happens in the SN2 reaction? The nucleophile attacks on the backside of the leaving group, and we are getting the product in which there will be a inversion in the stereochemistry of the product observed. So let's say here, so we have the leaving group iodine and nucleophile is the OH minus, right? So this OH minus is attacked direct exactly on the opposite side, and we are getting, you can see here, the inverted in the stereochemistry in the product. So this is the reaction, basically example of stereo specific. The specific word itself state we are getting specific product. So that's what. Another example, uh, similar examples we can see for these stereo specific reactions is like, let's say, this E2 elimination reaction. So here, uh, this is the one example of the E2 elimination. So this E2 means involvement of two, both starting material and the reagent involved. So this is a bimolecular, therefore we call it as a E2. In the earlier case also, why we call it the SN2, because there is involvement of the hydroxy, that is the reagent, and the starting material, that is two molecules are involved in the formation of the in the rate deterministic particularly. That's important. RDS. In the rate determining state, both reagent and the starting material is involved. So therefore, we call label particularly as the SN2. That is the nucleophilic substitution reaction. That is and bimolecular nucleophilic substitution reaction. That's the full terminology for this SN2 reaction. Okay, and E2 elimination is also the same involvement of the both reagent. Therefore, E2 elimination, and SN2 and the E2 elimination are the example of stereo specific reaction. If you look at the reaction mechanism in the E2 elimination reaction, so what will happen in the E2 elimination reaction? We need the this hydrogen and the leaving group anti-periplanar to each other. So what is anti-periplanar? So this leaving group and the proton. So you can see they are exactly on opposite side to each other. So these are the basically anti-periplanar to each other. We need to have this group anti-periplanar to each other. This is the main condition for the A2 elimination. And according to that, we are so this is just a redraw to just for understanding here. And so since this E2 elimination, the abstraction of the proton and the elimination of this leaving group uh, takes place in the concerted manner, and we are getting the product. So in which you can see this phenyl group directing opposite. So this is also example of stereo specific reaction. So these two SN2 elimination and it sorry SN2 reaction and E2 elimination. These are the example of stereospecific reaction. Specific itself state we are getting only one product. There is no other choice. Now, if you look at on the contrary, stereo selective reaction. So what is selective? Selective basically we get some selectivity in the reaction. So for that, the best example is in the next slide. I will show that one. So first of all, understand this. What is stereo selective? So reaction where one stereoisomers of the product form preferably over another. So this mechanism does not prevent the formation of other product. So basically, we are getting minor product as well. So that's also important. We are getting major product one, but also we are getting another minor product. And the best example to understand is this example. So, so in this example of the reduction of this ketone, so this is the example. So if you look at closely the structure of this, better I will just take it on the bigger screen for the same example. Okay, so this is example of stereo selective reaction. Selective itself indicates there will be some sort of selectivity, right? So here, so this is just a simple reduction reaction performed under, let's say, first of all, consider upon lithium aluminum hydride. So this is the lithium aluminum hydride is the source of hydride. So what we are getting from this reagent, we are getting hydride minus. Now, if you look at here, there are adjacent to this carbonyl group. This is the reacting site, but adjacent to the carbonyl, there is one methyl group directing upward and hydrogen directing downward, right? So hydrogen is sterically less bulkier compared to this methyl group, and therefore mainly the reactivity of this carbonyl center, reactivity on this carbonyl center of this lithium aluminum hydride is governed by the stereochemistry of methyl group. Now, when this lithium aluminum hydride, that is the hydride reagent, plus this group I am saying entirely, comes from the top side. What happened from the top side attack? Due to this bulkier methyl group, there will be some sort of steric hindrance. But when it comes from the bottom side, comparatively less steric hindrance from the bottom side. And therefore, hydride attacks on the bottom side is preferred. And in this condition, you can see here, we are getting around 75% formation of this product and 24% formation of this another product. So there will be some sort of selectivity. And this in the stereo selective reaction or this selective reaction, we can also improve the selectivity of this reaction. So let's say how we can improve. So we can change the reagent. So now what we did, we selected some more bulkier reagent. So bulkier reagent. So now this is the bulkier reagent. And in that case, the top side attack is very unfavored. Why? Because already our reagent is kind of very bulkier. So therefore, attack from of this hydride from the top side is not feasible because you can see here bulkiness of these groups, and therefore we are getting the attack of this hydride only takes place from the downside, and therefore we are getting 100% formation of this product in which the hydride is on the uh, bottom side, right? So this is example of the stereoselective reaction. So in the stereoselective, we can increase the selectivity. So ignore this distereo word for this instant. In the selective, this stereoselective reactions, we are basically getting selectivity in the product. There will be minor products, but major product is the we can get the improvement in the selectivity. So as in this case, by just changing the reagent, we can improve the selectivity. So you can see here 100%. So basically, this is the still example of the stereoselective reaction. Also, another example is we can change the reagent. So here, another example that I mentioned, that is the reduction of this alkyne. So in the reduction of this alkyne, what happen? If you use the H2PDC reduction, and if you look at the reaction mechanism of this H2PDC reduction, the mechanism itself involved. First step is the addition of hydrogen across the metal. So this is the basically metal. So hydrogen attached on this metal. Now the bond between both hydrogen get partially cleaved, and parallelly this olefin, sorry, the alkyne comes in contact with this hydrogen. So now this hydrogen transfer takes place to the alkyne. So if you look at the reaction mechanism, so basically this hydrogen transfer to the our alkyne in the same fashion, and therefore what we get the cis product as a major product. So this is the example of stereo selective reaction here. So here you can see we are getting cis product formation and trans product. Also, there will be obviously some chances like let's say reaction goes up to here, but not necessarily this only hydrogen involved in the formation. So there will be some minor product formation that is which involve the trans geometry, but the major product is the cis one in this H2PDC reaction. So how we can achieve? Let's say we want the trans product. So then we cannot use this condition. What we can go for this another condition, which is the sodium metal in the liquid ammonia. So this reaction mechanism go by radical mechanism. So and we know there will be, if you look at the burst reduction case also, the similar first electron transfer takes place to the center, and we get this here anion. So I will just go step by step for the radical this mechanism as well. So it will be easy for your understanding. So in this radical pathway also, so the sodium metal transfer electron to this alkyne. So what happen? And so this anion, this forms here, this bond goes here. So now what we have R C negative double bond C R. We have the radical. And since if you look at, so for instance, I will draw stereo, involve the stereochemistry also here. So let's say this R and R goes on the same side, and the anion goes on. Anion basically two electron, right? So this is negative charge, means that's what I have drawn here, two electrons and one electron. But if you look at here, in this case, there will be a steric repulsion between negative and negative charge. This is basically electron only, and this is also the two electrons. So there will be repulsion. So what happen? The major product will be this R C, sorry, C, and there will be the anion will be, let's say the negative charge will be here. Now this double bond, this goes are here, and radical forms in this lobe, which you know only one, right? So this geometry is preferred here. So in which case, in this case, what happen? The first, this is major. Then the second, as I mentioned, so from the alcohol, it can abstract the proton. So before abstracting the proton, so this can the first proton abstraction takes place here. Then the second step was the again sodium metal can donate another one electron to here. We get this R hydrogen. So now it became anion or the two electrons, and again the abstraction of the proton. So as like in the first step I have just directly shown here, this proton comes from this ethanol. Again abstract proton, we get the trans product as a major product. Why? Mainly because of this steric repulsion. So the cis product formation is not preferred in the in case of this mechanism. However, in the earlier case, as I mentioned also, here the cis product formation takes place. So this is the difference between the two reaction mechanism, and these two are also example of the selective stereo selective reactions. Okay, now this is about the stereoselective reaction, and also we have seen some difference between these stereoselective reactions. So these are basically in the stereospecific and the stereoselective reaction. The difference is like in the specific we are getting only one product formation, But in the selective, we are getting the major and the minor product formation. In the stereoselective reaction, the formation of product depends upon the stereochemistry of the starting material. However, uh, in the stereospecific reaction, formation of product depends upon the reactant. However, in the stereoselective, there will be a dependency on the several factors, as earlier also seen. In one example, here we have seen the stereochemistry depends upon the selectivity depends upon this methyl. Also, selectivity depends upon this bulkiness. So that several factors are there for the selectivity. That's about the stereoselective and stereospecific reactions. Now, uh, in the this asymmetric synthesis, there will be a different strategy to get the enantiomerically pure final product. The first strategy is the chiral pool synthesis, and the second one is the chiral auxiliary. The third one is mainly deals with the analytical purpose, which is the resolution. I will explain this resolution shortly, and then we'll see all these chiral pool and the chiral auxiliary method. So the resolution is basically, let's say I perform the one reaction. So these are my reagent which involve the uh, so whatever here this molecule, let's say like this. So I did some reaction, not like this. So yeah, so like this. I did some reaction and I'm getting these two product formation. Let's say this X and this is, so I'll better take some different color. Right, this one. Let's say I'm getting this X product and I'm getting this Y product. But now, since in this reaction, we are getting two enantiomers. Now, how to separate this one? So the first approach is you can use the chiral column and do the purification on the chiral column. So that's first approach. However, there are some limitation for this approach. Is like we cannot really load the more compound. So if you want to do the scale up, let's say kilogram scale up, kilogram scale, then that time we cannot really trust on the rely on the this chiral column method. So this chiral column method is okay for few mg to several gram scale. However, if you have the bulk scale product, if you want to do the in the several kg, 100 of kg, we need to purify this enantiomers. Now it is not possible with this chiral column method. So the chiral column is first type of first type in the resolution. Second is what we can do. We can convert these two compounds in the, these are in the enantiomer form. We can convert these two into the diastereomers, and diastereomers are separable. So what we can do, let's say the functional group. So here, so this B functional group, let's say for the instant, which is carboxylic acid. So in this case also, this B functional group obviously will be the carboxylic acid. Now we can do one thing. We can convert this carboxylic acid into the ester. But what we can choose, if you choose this enantiopure alcohol, what we are getting, so this will be alcohol will be enantiopure. Now what we are getting, we are getting the diastereomer in the product. Why? Because this is one chiral center, and it's the starting material, it also have the one chiral center. So these two chiral centers in the esters. So first chiral center was come from the here, it was somewhere here from the R1. So that is R1 is basically this entire group, right? So this entire group is the R1, let's say. So here one chiral center. The second chiral center is from the alcohol. So the second chiral center is from the alcohol. This is the first chiral center. It has the second chiral center. Now, so this diastereomers. So basically, when we convert this enantiomer mixture to their mixture of this acid to their esters, and this alcohol has also whatever the alcohol used to prepare this esterification is which is chiral alcohol. Now these two product form, we will get the formation of the two different products, and that two different products will be the diastereomers of each other, and the diastereomers are separable by column chromatography or other different methods. So diastereomers are easily separable, however enantiomers are non-separable. by normal method like crystallization or many, let's say, normal column chromatography. That method, enantiomers are not feasible to separate. But diastomers, there will be a different in the RF values. For the diastomer, if you just perform the TLC, the first diastomer will be here, second diastomer will be here. But if you have these are in case of the diastereomers. But in case of the enantiomers, what happen in case of enantiomers? So the TLC profile will be similar. Only we are getting only one spot. Here only there is mixture of this X also and Y also. So there will be no any RF difference for the enantiomers. So we can convert that our enantiomer into corresponding diastereomers, and at this diastereom stage we can purify these two compounds separately, and we are getting, let's say, whatever the X esters. So we can get that X ester back. Also this Y ester we can also get back, and later we can this just do the deprotection basically, and we can achieve our acid back. So what, which is our desired product here, so that we can take that back. So this is resolution method. So I hope I able to clear these basics here. Now we'll slowly move to the uh, chiral pool synthesis. So I think I will show the example of the resolution method here. So better just show the resolution method here only. So this is the example of the resolution method, and you can see now in my product what happened. I got these product. So whatever condition I got, let's say I have some starting material and I perform some reaction. I got these two products in the mixture form. Now what we can do, how we can separate this? So that will be uh, we can do by this resolution method. So this is another method what we have what they have did here. They have treated these startings. Let's say this is I give the label it as a R and S. So basically they are R and S comes from the this stereochemistry of this chiral center. So for our understanding simplicity, so this is R product and this is S product. Now we want to separate this R and S both product from each other. So this method, what they have did, they have mixed this with the ephedrine molecule. So this is the one of the chiral reagent. And what happened? So when they mix this with the ephedrine, now this R product forms a crystalline salt with this ephedrine. So you can see here, so this is the crystalline salt. However, this S isomer plus ephedrine, which is soluble. So what we can do, we can just in the reaction mixture, we can just add the, so react what in the mixture, we can add this ephedrine, stir this for some time. What happen? After some time, it form the crystalline salt. Particularly, these R isomer only form the crystalline salt. However, the S isomer doesn't form any crystalline salt. Then what you can do, we can just do the filtration. So we get the crystalline, whatever the compound in our hand, that will be this one. However, the non-crystalline one, the soluble one, what we can get will be in the liquid form. So this will be the solid. This will be remain on the filter paper. However, this compound will be go in the filtrate. So sorry. So this is also one method of the resolution. So any doubt in this one? So there are several methods. One crystallization, second one is the purification by, let's say, HPLC by using the chiral column. Not only HPLC, there are nowadays there are some. If you look at the purification methods, generally organic chemistry they generally purify by crystallization or column chromatography, and in small scale, mainly the HPLC is the good for the synthesis purification of such chiral enantiomers. However, in the bulk scale, the HPLC is not really feasible. So in that case, instead of using normal silica for the column chromatography, if you use some stationary phase in such a way that which will be a chiral stationary phase. So I'm not sure whether this such chiral stationary phase are commercially available. I mean, at low cost at least. Commercially, they are available, but however, the cost at this moment is quite high for these chiral stationary phases. So this another approach that which is the crystallization method also. So one can form the co-crystal. However, another will be not form. So therefore, in this case, we can do the this crystallization method of this resolution. We can get the crystal of only one enantiomer for this particular case. So this is like the one of the real life example of the resolution. So by using this co-crystallization methods. Now let's move to the our another. Let's go back to the our strategy. We'll see main thing chiral pool and the chiral auxiliary. The first one is the chiral pool. So this chiral pool is the most preferable tool in the enantiomerically pure molecules. And common chiral starting materials are generally derived from the amino acids, carolic acids, or the monosaccharides, that is the carbohydrates. So these are the natural amino acids. So this is natural L amino acids. However, uh, this is the very quite cheap. So this also one of the uh, starting material for the this chiral pool synthesis. Further, there is alpha hydroxy acids, then the D sugars. So this L amino acid, which is naturally available. However, D sugars are naturally available. So that that you have to remember. Maybe some you can get some question may at some point for the competitive examination. All available amino acid they generally uh, present in the L form, and generally the carbohydrates naturally available they are in the D form. So by using this chiral amino acid, so this is the L-serine synthesis can be done by such chiral pool approach. Oh, sorry. So this L-serine also one of the, I think the starting material you can use for the chiral pool synthesis. We'll see some example then and then only we can able to understand. So basically this chiral in this approach, what happen? So generally the commercially available some sort of starting material we select as a starting. Uh, and from that starting the center that we carry toward till the end of our synthesis. So let's see some example. Let's take a simple example. If you want to have the synthesis of some, let's start from very simple for one step synthesis. So this is our target molecule in which you can see there is a chirality involved. So what we can select in this case, what we have did, we have selected the starting material itself has the chiral center. So you can see, so it has the chiral center here. So this chiral center, we have taken this amino acid which has this chiral center already present. Then what we did, we did the reduction of this acid, we get our target molecule. So this is just one step synthesis. So, and this you can see the chiral center was present in the starting and we have carried this chiral center till our final product. Similarly, this is the starting material we have taken and we want this alcohol. So we have selected this starting which involve, you can see this is enantio pure that I am highlighting enantio pure. So this is enantio pure amino acid that we have taken and then only we can get this enantio pure product. That is the isomer which involve this stereochemistry of this center. So what is stereochemistry here? 1, 2, and 3. So this is S stereochemistry. So we have kept the stereochemistry. We have taken the starting also. We are the center. The stereochemistry here was the fixed. So that's what we have taken here. So here, second example, this was the first example of this chiral pool synthesis. If you look at the second example, you can understand this functional group was amine earlier. So what we have did, we have treated with this NaNO2 HCl and then did the hydrolysis. What we get? We get this alcohol. So I will not go into detail with the how this reaction goes. So NaNO2 plus HCl, what it does with the NH2 functional group and how we can get this one. But yeah, this is the product we are getting with this in this reaction condition. So we have selected starting material in such a way that our required stereochemistry will be there in the our final product. So this was also enantiopure. I will draw the short form for enantiopure, EP. So easy for understanding.
Excuse me, sir.
Enantiopure. Yes,
Hello.
please.
Sir,
Yes, you can. Yes.
the amino acid from amino alcohol, how it can be amino alcohol? Yeah, no amine group, sir, please. This one, last one, yeah.
Okay. I think the name itself it's incorrect. Yeah. Yeah. The name it should not be the amino alcohol. The amino alcohol name that's generally the common name. So mainly that derived from the amino acid. Therefore, this they use terminology this amino alcohol. But right now you can just ignore that one. So this is basically chiral pool. These two syntheses are like a chiral pool. So the starting material stereochemistry you have selected from the starting, and that carry forward uh, toward the end of this or product. So I will show some more complex example. However, I will not explain all steps. So you can refer the slides later. Right now, this is another example. So the stereogenic center is retained in this example, and all other centers are destroyed. So let's say, so this is the stereo center we are focusing on. You can see, sorry, yeah, you can see here in this molecule, the highlighted in the red one. So this center, I don't know whether you can able to see the pointer or not. Okay, so you can see this center is we have in the starting and in the product. So that center is retained, and to get from this do sorry 2 dehydroxy sorry 2 deoxy D ribose to R sulcatol. So they have did this chiral pool approach. So the center from the starting, the chiral center which is present from in the starting material will be retained till the end of this reaction. So if you look at the reaction mechanism, the progress, all the steps involved in this one. So the first step, I will just quickly explain this one. So the first step is the methanol plus acid and the methyl. So in this case, what happened? Methyl protection was done here in the first step. The second step is the methanol. Basically, here is the solvent. Oh, sorry. Yeah, in acidic condition, I think so. This the lone pair on the oxygen can involve. Sorry, this is too weak. So if I just show some mechanism for this one, what happen? This in place of the acid, what happen? It can convert it to H3O plus, right? So this will be OH2 plus. Now it is good leaving group, and also if you look at the lone pair on the oxygen, can goes here. This can eliminate. So this is basically SN1 elimination reaction. Now what happen? Once this eliminate, the methanol, Me, OH attacks on uh, this center. So this is already eliminated. Now there will be double bond. Now the methanol attacks on this center and we are getting the methanol here. The stereochemistry of this center will not be fixed because this is SN1 reaction, attack from the top side as well as attack from the bottom side. Both are possible here. However, at this stage, we are not really worried about this chiral center, stereochemistry of this center. So we are getting methanol here. And further, in the second step, what we have did the mistile protection. So that's what we did in the first step, right? So this is the basically first step. The second step is the Ki and the Raney nickel. So not sure how this reaction work, the mechanism, how the Ki and Raney nickel basically eliminate these both two groups. However, in this reaction, this is the product we are getting from. So you can look at some ChatGPT and all to how this mixtile reproduction occur with this potassium iodide and the iron nickel. The next step is hydrolysis. So what happen? This is now methanol. If you treat with the water, again this can be converted into the OH back. Further, what happen? So this one is in the equilibrium. So you can see these two compounds are in the equilibrium. How this will be in equilibrium? So this hydroxy group OH now can go here in the form of double bond and this bond can be cleaved. So we are getting this OH here, right? And at this stage, since there is one hydrogen was present, so you can see here there should be one hydrogen. So this converted to the aldehyde. So what we get? We get this once this bond get opened up, we are getting this formation of the alcohol. The chirality or the any stereochemistry doesn't change at the center. This center will be stereochemistry remain constant. Now this aldehyde plus this Wittig salt, what happened? So not Wittig salt. Yes, it is Wittig salt. That is the PPH3. PPH3 with CH. This is the basically Wittig salt. This Wittig reaction, we get this olefin formation, right? So basically, from the starting material to this product, the stereochemistry of this chiral center remained constant. So this center, the stereochemistry remained constant. So this is basically a chiral pool. So the pool word itself, you can understand the stereochemistry we have carried directly from the starting till products. No matter whatever step we have did, but the stereochemistry will be retained in the final product, have been retained in the final product. And that's what the chiral pool approach. So this is the example of the chiral pool approach. So any doubt here other than the mechanism of this Raney nickel and this Ki? So that I also don't know how this actually the how this OMS deprotection takes place with this Ki and Raney nickel. Other doubt you can ask now, ask me.
It's okay, sir.
Now we'll see some more example with involve some similarly chiral pool approach. So the retrosynthesis of this is basically the reverse that you should able to understand. Although I'm here examples showing the synthesis example of synthesis, but the retrosynthesis is basically exactly opposite. Then you can just refer back that how we can do the retrosynthesis of this molecule. Okay, now at this point, it is important to understand what is chiral synthesis. Then and then only it is feasible to understand what is the retrosynthesis of these chiral compounds. So another example which involve the functional group interconversion plus chiral synthesis, chiral pool. Chiral pool. So this is the synthesis of the L-glyceraldehyde the unnatural sugar from the amino acid L-serine. Okay, so as also I mentioned earlier, where here the natural amino acids are present in the L form. However, the sugars present are in the D form. So that's what I want to highlight here. Now move to our example. So this is the chiral pool synthesis of the L-glyceraldehyde from unnatural sugar from the unnatural sugar. So this is the unnatural sugar which is not really synthesized by the nature from the natural L-serine. So this is L-serine is basically amino acid. Obviously, it is L. So this is the example of the sorry. This is the L-amino acid. So this is L-serine natural amino acid, which is chirally pure and very cheap. Now we want to synthesize this L-glyceraldehyde. The D-glyceraldehyde is very cheap. However, the glyceraldehyde is very expensive. So this is very cheap. But if you want to synthesize this L-glyceraldehyde, now we have to use this chiral pool synthesis approach. We will see how we have retained the stereo center of this starting serine in the product. So this is the stereo center you can see. So if you look at here, this is the stereo center, and this comes from the L-serine. So this is the structure of L-serine. The first step is NaNO2 HCl water. So that earlier same step, this converted to the corresponding hydroxide. So you can keep remember this reagent also. So what exact mechanism you can look for that one. Right now I am showing directly NaNO2 plus HCl plus water. It gives this amine to the alcohol. Retention in the stereochemistry in this stage. Now what we have did, we did the diol protection. So the catalytic amount of Lewis acid, this is paratoluene sulfonic acid plus acetone. So we can do the with the acetone 1,2 protection. So this is a so these two alcohol can react with this ketone. So CH3, CH3 impresses the catalytic amount of acid. So this acid basically polarize this OH bond. So this double bond of this ketone polarized, and therefore this hydroxide sorry attack on the carbonyl centers, first attack, and the second attack gives the protection of this diol. So if you want to protect 1,2 diol, use the acetone, right? If you want to protect 1,3 diol, so that's the question for you guys. So if you want to protect 1,3 diol, then what type of alcohol we can use? But right now we want to protect 1,2 diol. So for protection of 1,2 diol, the acetone is the best protecting reagent. Acetone plus PTSA, palatolene sulfonic acid. So this is basically the uh, what you can say, less strong weak acid. Okay, so we have did the protection, and now what we did the BHT or the LiLH4 reduction. Basically, this is the when we are also seen the what are the reducing reagent. I have already covered. If you want to reduce the alcohol, so this BH3 is the best reagent. So we have reduced this acid to alcohol directly by using the BH3 in the THF solvent at 0 degrees Celsius, right? Or we can also use this LiLH4. Okay, so we get this alcohol. Up to here, okay. What we can do now, we can convert this into the aldehyde. So you may mention why you have stopped this reaction of the reduction of the alcohol to the aldehyde stage. So stopping reduction of this acid to this aldehyde stage is not really what you call synthetically feasible steps. So in presence of this LiLH4 or the BH3, we get the directly the alcohol, and there will be some intermediate we can isolate that one. However, that will be we can stop the reaction of this acid to aldehyde stage also by manipulating the equivalence of this BH3 or the LiLH4. Okay, but anyway, instead of that, we can directly convert to the alcohol, and just by the PCC reduction, PCC oxidation, we can now get that aldehyde back. So this is the most feasible. Directly convert to the alcohol. This acid directly convert to the alcohol, and then by using this PCC, we can get the single spot this aldehyde. Now, what we can do? We can reduce the deprotect this. So whatever the protected alcohol, this was the alcohol protection, so that we can deprotect by using the water and acetic acid. So just stirring at the room temperature with the water and acetic acid, we can get this aldehyde back. So this is the synthesis route for the L-glyceraldehyde, which is a unnatural unnatural glyceraldehyde, right? So this is what the synthesis, and this approach, as you can see, the chiral center we have written from the starting to the product. Sorry, here is right. So this is the example of chiral pool synthesis. So I will show some examples of this one because it is very important concept. You don't really, you can also from this course you can also see some asymmetric synthesis part also you can able to take from this one, because at the end we need to uh, get expertise into the synthesis, whether by through the retrosynthesis or the chiral synthesis or asymmetric synthesis, it doesn't matter. Okay, another example here is the in a so this is the chiral full synthesis of essential amino acid L-serine from the natural non-essential amino acid L-serine. So this is the L-serine, and we want this L-serine, sorry, L-lysine. From this L-serine, we want L-lysine. Now what we can do, so in this case, this entire stuff is constant. So this chiral center from the starting and the product is kept constant. So there are several steps in all. However, in all steps, there will be, we are not touching the, or we are not disturbing the stereochemistry of that stereo center. So the first step here, so this is the L-serine. What we can do, the first step is CBZ protection. So we did the CBZ chloride plus the base, the CBZ protection we did, then followed by the second step, which is the coupling of this acid to ester formation. So that's what we have did, acid convert into the corresponding ester. Now the another step is the PCC oxidation. So this alcohol functional group convert into the aldehyde functional group by using the PCC oxidation, right? Another, from this, once we get the aldehyde, we do the Wittig reaction on the aldehyde. So what we get? So we have started reacted this aldehyde. So this is the aldehyde. So this aldehyde, when it react with the this Wittig, so we are getting this Wittig reaction at the center. You can see. And once we did this Wittig reaction, we can do the deproduction of the CBZ. CBZ deproduction we can do with the help of H2 palladium on supported on the carbon, H2PD and the methanol solvent. So we can do the CBZ deproduction. So we get the L-lysine. Any doubt in this example? I will share the. I hope you guys are able to access the OneDrive which involve this all this PPT. Are you getting this updated all the PPT for all weeks? So I have once shared the link for the OneDrive, and I think you guys are getting the link for the drive from the NPTEL by mail also. So we will stop here for today. This is all about the some examples of the uh, examples in all the chiral synthesis. In the next video, what we can do further, we can see from the next class onward. we take one example, one or two. I will just directly give the today only. You can refer this example. I will not explain the next video. This is just the example of the same chiral pool synthesis. From the next week onward, I will move to the asymmetric synthesis, which involve the chiral auxiliary. So I hope you understand something at least regarding this chiral synthesis or the asymmetric synthesis. And the basically retrosynthesis is just reverse you can do for this one. For at this stage, I believe it is easy to understand the synthesis instead of directly going to the retrosynthesis. So thank you so much for joining. And if you guys have any doubt, please let me know, or we will stop here for today.
Thank you, sir.
Okay, we'll stop here.
Uh, uh, oh, hello,
Sorry,
hello.
yes, you can ask.
Sir, may I tell if the time of this session is little bit change? If you have any problem, sir?
Actually,
I am unable to attend each week. This time it is impossible for me, so I miss
uh,
the class regularly. If
Actually, the issue is like the NPTL, they generally, whatever NPTL team, they have shared time. I have also have the compulsion to take at the same time.
yeah,
So the issue is,
if the time
but you can, I mean, access the YouTube video, right, for the recorded session.
yeah, but there
You
is
can,
no live interaction.
okay. So
The
if you
time
have,
is from 7 to 8. Actually, 1 hour class is happening. Took place actually. So if it
uh,
is from 7 to 8 or 9, that will fine for me. Otherwise, regularly I miss the class. But I want to attend the class.
maybe if you join some late also, but you can ask the doubt from the last video in this video also. There is no any issue. I can dig out. I mean, I can take the other earlier slides also. That's why I can. I generally take last week slides. If you able to not able to join live, then if you but you have the doubt from the YouTube video, whatever the uploaded video, recorded one. So you can ask me in the next video also, or sometime you can join after 8, right? Or sorry, after 7, or not like that.
Okay, okay, sir. Thank you.
Yeah, mainly the actually the restriction is like we have to start compulsory session at the 7 o'clock. I mean, I remember one day, I think 2 weeks back, I missed. Uh, I somehow I not able to join, but and the NPTL team they have asked me to not to uh, vary the time of the of the class. That's what.